Here we have the Lewis electron dot structure of carbon dioxide. What is the electronic geometry of carbon dioxide?
Well, to figure this out, what you have to do is look at the central atom. How many electron regions are around that central atom?
2, 1 here and 1 here.
Right, because a double bond is one electron region. So that's one region, there's another region. So you tell me, what's the electronic geometry?
We can tell, because there's no lone pairs, that it's linear.
So here I've got a model where I've imagined here's your carbon, 2 oxygen atoms, and if this double bond represents one balloon and then another double bond is another balloon, they're getting as far away as possible. We see that line. So the electronic geometry is the line. So what's the molecular geometry?
Well, because this atom has no lone pairs, it's the same as the electronic geometry. So, as you can tell from this model, the molecular geometry is linear.
And what is the bond angle?
If you take our molecular geometry and you imagine as a circle, there's 2 atoms. You divide the whole circle, which is 360 degrees, by 2. You have 180 degrees, which gives our bond angle of 180 degrees.
So is this molecule polar or nonpolar?
Well, if we look at our VSEPR model kit, we can tell that these 2 molecules are the same. They're going to have the same electronegativity, but because they're oxygen, they're going to have a slightly higher electronegativity than carbon. They're going to pull apart, but this pull is going to be equal and opposite, so it's going to be nonpolar. But here, what is the hybridization?
Hybridization, because you have 2 regions, it would be sp linear, sp hybridization.
Here we have the electron dot structure for ammonia. What is the electronic geometry?
Well, to figure that out, we have to figure out, well, how many electron regions are around the central nitrogen? A lone pair of electrons is just one region. A single bond is one region. So we've made a model using balloons where here this balloon represents 2 electrons that are not bonded. This is one region. This balloon represents a lone pair of electrons. Lone pair of electrons are just non-bonded electrons that actually take up space, and they even repel bonded electrons greater than other bonded electrons. So they take up even more space than the actual bonding electron regions. So here we have 4 regions, 1, 2, 3, 4. This forms a tetrahedral electronic geometry.
So here, the molecular geometry, because we have this lone pair, the molecular geometry is not the same as the electronic geometry. The molecular geometry here is trigonal pyramid.
Yeah, so here we've got the model. And the molecular geometry is, what does this molecule look like when you don't take in consideration the electrons? What does the molecule actually appear to be? It appears to be a trigonal pyramid. Notice it's not all on the same plane. This nitrogen atom is up higher than the plane of the hydrogens, so this is a trigonal pyramid molecular geometry. With bond angles, what are the bond angles?
Well, here we go back to the electronic geometry. So if we have 4 regions of electron density, that gives us a bond angle of 109.5. But here, because this lone pair takes up a little bit more room, it's a little bit less than 109.5. So is this a polar or a nonpolar molecule?
Well, this would be a polar molecule because we have a net region of negative on the nitrogen and a net region of positive on the hydrogen atoms. If we imagine a nitrogen more electronegative than hydrogen, that nitrogen's pulling electron density towards itself. If this molecule we were playing tug-of-war with hydrogen, there would be a net movement of dipole, net dipole towards the nitrogen, polar.
So, for this molecule, what is our hybridization?
The hybridization would be 1, 2, 3, 4 regions, so it's sp3.
Now we have the Lewis electron dot structure for boron trifluoride. Here, what is the electronic geometry?
Well, there are how many electron regions around the central atom?
1, 2, 3. 3 regions of electron density around the boron.
Right, because remember, a single bond is one region, a double bond is one region, and a triple bond is one region, and a lone pair of electrons is one region. All we're looking at is the central atom. All we have are 3 single bonds, so it is electron geometry trigonal planar. What is the molecular geometry?
Well, for our molecular geometry, it's sometimes easier to look at something like our VSEPR modeling kit. Here, because there's no lone pairs, it looks exactly like the electronic geometry, so it's still trigonal planar.
What are the bond angles?
Well, we can do the same thing we did last time. We take a circle, divide by the number of atoms, which here's 3. So 360 divided by 3, that's 120. So we have 120 degrees between here, then here, and here. Is this molecule polar or nonpolar?
Well, we know that fluorine is more electronegative than boron, so we have polar covalent bonds between each of these boron and fluorine atoms. But is the overall molecule polar or not? Well, is there a net region of negative or positive on one side of the molecule? No. Each one of these fluorines are pulling equally and symmetrically, so let's play tug of war. Each one of those fluorines, let's put it back on. Each one of those are pulling the same. We're at a standstill, therefore we'd say that all the bond dipoles cancel out. It is nonpolar.
So for this molecule, what is the hybridization?
The hybridization is 1, 2, 3 regions, so it's sp2. sp2 hybridization.
So our molecule here is methane. This is the Lewis electron dot structure for methane. What is the electronic geometry?
Well, how many electron regions do we have around the central carbon?
As you can tell from our balloon, there's 1, 2, 3, 4. So that makes the electron geometry tetrahedral. For our molecular geometry, as you can see, our central atom has no lone pairs, and from our modeling kit, we can tell that the molecular and electronic geometry are the same, making them both tetrahedral. So what is the bond angle for this molecule?
So when we look at the electronic geometry of this molecule, 4 regions getting as far away as possible are going to form 109.5 degree bond angles. So this is 109.5, 109.5. Every one of these bond angles are 109.5 degrees.
So is this molecule polar or nonpolar?
The molecule is nonpolar because carbon and hydrogen have very similar electronegativities, so we don't even have polar covalent bonds, and they're all equal and symmetric, so nonpolar.
What about the hybridization for this molecule?
Hybridization, we have 4 regions, sp3. sp3 hybridized orbitals form this geometry tetrahedral.
Now we have the Lewis electron dot structure for water. What is the electronic geometry?
We look at the central oxygen. That central oxygen atom has how many electron regions around it?
4. 1, 2, 3, 4.
Right, so if we use balloons to represent the non-bonded lone pairs of electrons around that central oxygen atom, they're taking up a little bit more space. They're repelling a little bit more than our bonded electron regions. And we see the electronic geometry, 1, 2, 3, 4, would be tetrahedral. Tetrahedral electron geometry. It includes the lone pairs of electrons. So what's the molecular geometry?
Well, for this, we look at our molecule and without our lone pairs. So here, our molecular geometry is bent. We have a bent molecule.
With a bond angle?
Here, the bond angle is, you take into account your lone pairs. So, with our lone pairs, it forms a tetrahedral, which is the 109.5. Because of the lone pairs, it's less than 109.5. So our bond angle is less than 109.5.
So yeah, just a little bit less than 109.5 degree bond angle. Is it polar or nonpolar?
Well, because of our regions of electron density with these 2 lone pairs, the oxygen is pulling more electrons towards it, so it is a polar molecule.
Right, so there's a net region of negative up here and net region of positive down by the hydrogen. So this oxygen is more electronegative than hydrogen, pulling electron density towards itself. If we're playing tug of war, it moves. There's more electron negative region on that oxygen. It's not equal and symmetric. This is a polar molecule. Very, very important in chemistry to understand that water is a polar molecule. Has a net region of negative and a net region of positive. And what is the hybridization?
Here, because there are 4 regions of electron density, it is sp3.
sp3 hybridized. 1, 2, 3, 4. 4 regions, sp3.